The Haber-Bosch process, a revolution in industrial design. A world on the brink. At the start of the 20th century, the world faced a critical challenge. Population growth surged and food demand outstripped supply. Traditional agriculture was faltering, unable to sustain a growing number of mouths. A radical solution was essential. This urgent context birthed the Haber-Bosch process, an invention that would transform agriculture and revolutionize industrial design. Historical context: fertilizers and the agricultural dilemma. In 1909, German chemist Fritz Haber focused on nitrogen, key for plant growth. Natural nitrogen sources, mainly atmospheric and limited mineral deposits, could not meet soaring agricultural demands reliant on a few nitrogen-rich fertilizers. Haber proposed synthesizing ammonia from nitrogen and hydrogen, despite the challenge of breaking inert nitrogen bonds, which comprise 78% of the atmosphere. Engineering challenge: the synthesis of ammonia. Haber's ambitious idea was theoretically robust. Ammonia could produce urea and other compounds essential for crops. However, he needed a feasible method to produce ammonia industrially. Partnering with engineer Carl Bosch at BASF, they aimed to create an efficient, economical approach. They tackled heat and pressure conditions, catalyst design and material constraints. Designing the process, chemistry and physics. The Haber-Bosch process required specific conditions to favor ammonia formation from nitrogen and hydrogen gases, described by the reaction N2G plus 3H2G right arrow 2NH3G. High pressure and elevated temperatures were essential. Iron catalysts facilitated breaking the nitrogen triple bond, a key barrier. Key design steps included: 1. Catalyst development. Iron was chosen for its efficacy and availability. Enhancing activity with potassium and aluminum oxides improved efficiency. 2. Temperature and pressure management. Optimal conditions had to balance temperature and pressure, around 450 to 500 degrees C and 200 atmospheres, demanding robust materials. 3. Reactor design. They needed large-scale reactors capable of sustaining harsh conditions. Early designs evolved from tubular to multi-stage reactors, enabling continuous flow. Overcoming difficulties, a collaborative endeavor. The journey to the Haber-Bosch process faced significant hurdles, notably sourcing cost-effective hydrogen. Early methods included electrolysis and methane reforming, initially favoring methane cut costs but increased carbon emissions, raising sustainability concerns. Environmental ramifications loomed as production scaled. Bosch's engineering vision effectively merged chemical and mechanical design, culminating in the first commercial plant in 1913 in Oppau, Germany, fundamentally reshaping industry. Key systems: the engineering symphony. The Haber-Bosch process exemplified a blend of engineering systems. 1. Reactor systems. Early cylindrical reactors had stacked catalysts for efficient heat transfer, constructed from specialized steel alloys. 2. Heat exchange systems. Effective cooling and heating systems maintained optimal temperatures, utilizing counterflow heat exchangers to reclaim energy. 3. Separation processes. Ammonia separation from unreacted gases involved condensers for recycling purposes. 4. Automation and monitoring. Early automation integrated pressure gauges and thermocouples, enhancing efficiency and safety for future processes. Breakthroughs and evolution. Impact on industrial design. The Haber-Bosch process set a precedent for linking complex chemical reactions with large-scale engineering, inspiring future industrial innovations. Plants showcased modularity and adaptability, influencing design standards across petrochemicals and pharmaceuticals. Real-world impact. Feeding the world. This process revolutionized agriculture. Soaring fertilizer production correlated with crop yield increases. An estimated half of the world's population now depends on food supported by Haber-Bosch fertilizers, driving urbanization as rural communities transition to cities. Furthermore, nitrogen's role extended beyond agriculture, spurring advancements in plastics and pharmaceuticals. Yet the widespread adoption of nitrogen fertilizers raised concerns about soil health, water eutrophication, and biodiversity. These issues now dominate sustainability discussions in engineering. Reflective closing. The legacy of engineering ingenuity. The Haber-Bosch process epitomizes engineering brilliance, merging chemistry and mechanics in an unprecedented manner. It illustrated the power of human innovation to address global challenges, reminding us of technology's environmental ramifications. Reflecting on this milestone underscores the necessity of balancing technological progress with ecological stewardship. The lessons from the Haber-Bosch development remain crucial today as we confront food security, resource management, and sustainability issues. The ingenuity of Haber and Bosch is a guiding inspiration, emphasizing the vital interplay of science, ethics, and design in shaping humanity's future.